Okay. So, let us get started and we will continue our discussion from the point we discussed last time. So, if you remember, we were discussing about task scheduling in multiprocessors and distributed systems. So, we had said that for uniprocessors we could discuss just two algorithms. One was a optimal scheduler for static priority algorithm and for dynamic priority algorithm, and that summarized our discussions on the uniprocessor system. But for real time scheduling on multiprocessor and distributed systems, it is a NP hard problem, and we have many heuristic solutions proposed over years, and some of them are popular, and we are going to discuss only a few popular scheduling solutions. And we had said that there are two categories of task assignment algorithm. The task assignment needs to be done before the tasks can be scheduled on the individual nodes, and the assignment can be static or dynamic. In static, we are going to discuss three algorithms: the utilization balancing algorithm, which can be used for EDF and we can modify it to use for RMA, the next fit algorithm for RMA, and the bin packing algorithm for EDF. These are three static solutions, just sample static algorithms we will discuss. Not by no means we are saying that these are the best algorithms that are available. What we are saying is that these three are popular algorithms. Many variations of these algorithms exist, and similarly for dynamic there are many scheduling solutions that have been proposed. We are just discussing two of them: the focused addressing and bidding algorithm and the body set algorithm. In the utilization balancing algorithm, we had seen that we need to maintain a task queue which has the tasks in increasing order of their utilization, remove the tasks one by one from queue and allocate it to the lowest utilized processor. Each time you take a task out of the queue, examine all the processors, find the one which has the lowest utilization and just allocate it to that. Simple algorithm. And here the node utilizations are not really perfectly balanced because of the allocation. It is likely that if the last utilization, if the last task has a very high utilization, let us say 0.5, then definitely if it goes to some node, it will make it change the utilization to very high values, is not it? So, here this algorithm is used when the nodes individually are scheduled using EDF. We had said that is because we are not really having any other restriction here in the form of the Liu Leyland or Liu Lehoczky's criterion. But you might ask a question that why do we maintain the tasks in the queue in increasing order of their utilization? Why not in decreasing order of their utilization? What will be the impact of that? If we maintain the task in decreasing order of utilization, and then first the high utilization tasks are assigned to the nodes, right, and later the ones that have smaller utilization they are allocated, won't that be more balanced? It is not very difficult to find that out. So, let me give it as a bonus problem that please write a small program that will generate tasks of various utilization, and then it will automatically allocate using this algorithm. One is they are maintained in a queue where they are ordered in increasing order of their utilization, and another one where they are ordered in decreasing order of their utilization. please check which one, because we said here that this is the figure of merit of the utilization balancing algorithm, which one will lead to more balanced utilization or will have a higher figure of merit. What about random arrangement of tasks? What is the performance of that? We will have to do that for large number of task examples, is not it? We have to automatically generate tasks with various utilizations. Not a very big task actually to check this out. Small program, maybe some 20-30 line of C program, which will generate the tasks, and then it will check which algorithm will work better, whether the variation where the tasks are maintained in increasing order of their utilization, decreasing order of their utilization, or random order of the tasks, and by how much which one will be better on the average. Please try to find that out and submit it to me. Now, let us look at the next fit algorithm used in conjunction with RMS scheduling at individual nodes. The essence of this algorithm is that tasks with similar utilization are allocated to the same processor. You might ask that see what is the idea behind this? I mean, why should tasks with similar utilization be allocated to the same processor? I do not know exactly what is the meaning of this heuristic. It is basically a heuristic assumption that if tasks with similar utilization are allocated to the same processor, possibly the schedulability is higher, possibly, but why it is not, I do not have an answer. Please think about it. If you find the answer, just let me know.
Similar utilization means equal?
No, we will see similar means, let us say some task has high utilization, let us say 0.8 to 0.1, let us say these are considered as high utilization. So, then they are one class of task, then let us say 0.5 to 0.6, they are similar, right, 0.1 and 0.2 utilization, they are similar. So, for different classes of utilization, we will keep a processor reserved. For 0.8 to 0.9, we will have some processors, 0.5 to 0.6 we will have some processor, 0.1, 0.2, 0.2, 0.3, etc. So, those we say that they have similar utilization. The different classes of utilization have similar utilization, and we will keep a separate node for them for running. But why should similar utilization tasks run on the same processor? It is not very clear. You please think about it. If you find a logic.
All the process of similar utilization will have equal chances to execute. If there is a high utilization one and the lower utilization one, the chance that lower utilization will get extended.
No. See, as you know that the rate monotonic algorithm are for individual nodes, and here the priority of the tasks is based on the period, not on the utilization, is not it? So, what you are saying quickly is not really correct. So, it is not necessary that you give the answer right now, because I said that it is not a very straightforward problem. Think of it. If you think of some good answer, just let me know. It is not mandatory that you will have to answer it right now. So, if we have n processors, we will create n classes of tasks. For each class of task, the processors have similar utilization. We will say that a task belongs to class J if 2 to the power 1 by j plus 1 minus 1 is less than ei by pi, which is less than equal to 2 to the power 1 by j minus 1. This term, if you see 2 to the power j minus 1, it will ring you about the Liu-Leland criterion, is not it? 2 to the power 1 by n minus 1, n into 2 to the power 1 by n minus 1, right. So, that may be a hint. Please try to think in this direction, that for Liu-Leland a task set to be schedulable, is n into 2 to the power 1 by n minus 1. Possibly the developers of this algorithm, those who proposed this, they had some hunch or some hint from the Liu Leyland algorithm, where we had the bound on the utilization for a processor to schedule n number of tasks is n into 2 to the power 1 by n minus 1. And if we have n processors, we need n classes. So, the first class will have 1 by 2 minus 1, right. So, that is 0.4, is not it, 1.414, is not it. 2 to the power 1 by 2 will be 1.414, minus 1 is 0.41 to 1 by 1 is 1, 2 minus 1, 1. So, between 1 to 0.41, that will be the first class that will be constructed, is not it. So, the first one processor will be reserved for those tasks which have utilization between 0.414 and 1. The second processor will be 1 by 2 plus 1, that is 1 by 3. So, 2 to the power 1 by 3 is how much? 1.3 something, I guess, 1.3. So, between 0.3 to 0.41 will be for the second class. The third class will be 1 by 3 plus 1. So, that is 1 by 4, 1 by 4 will be something like 1.2, right. So, between 0.2 to 0.3 we will have another class, that is the algorithm, and the last class will be between, let us say, for 4 processors, the last class will be between 0 to 0.2 or something. So, if we think of this algorithm, it actually defines grids of utilization. If it falls in some grid, then it belongs to that processor. So, these are, if we have 4, we are trying to construct 4 classes. The first one is between 0.41 to 1. The class 2 is 0.26 to 0.41. Class 3 is 0.19 to 0.26, and the class 4 is 0 to 0.19. So, if you show this on a grid, you will see that 0.41 to 1, this belongs one class, and 0.26 to 41, this is another class, 0.19 to 26, this is a small grid here, this is another class, and 0.0 to 0.19, this is another class. So, depending on the utilization, you put them into certain class, and then for each class you have one processor running those tasks. This algorithm works well actually and requires 2.34 times the optimum number of processor. So, if you want to schedule using RMA, you do not really need to balance their utilization. Utilization balancing may not be a good solution for this, is not it. So, if the number of tasks is small, through and you can write a program which will try out all possible of the combinations of the tasks, right. For smaller number of tasks, it is possible to compute all possible combinations of the tasks, and then you can see that for the optimal one, which you can compute based on all possible task combinations, this solution is 2.34 times the optimum number of processors. We have the bin packing algorithm, which is used when the nodes are individually scheduled using EDF. Bin packing is a standard problem, all of you know. The problem is that we have set up tasks and we just keep on assigning them and to the different processors, just like you have the bin packing algorithm. We will discuss two variations of the bin packing algorithm. One is called as the first fit random algorithm and the other is the first fit decreasing algorithm. In the first fit random algorithm, the tasks are selected randomly and they are assigned to the processors also arbitrarily. So, they will keep on assigning to the processors as long as the utilization of the processor does not exceed 1. The performance, it performs easy to find through a simulation experiment, at most 1.7 times the optimum number of processors required. The first fit decreasing algorithm, here the tasks are sorted in non-decreasing order, selected one by one, assigned to the processor to which it fits in, and this performs worse as compared to the random algorithm. No, I am sorry. So, the first fit random is 1.7 and this performs much better compared to the random algorithm, takes 1.2 times the optimal number of processor.
Sir, can you explain this? 1.7 times the optimal number of processor or 1.22?
Okay. See, the optimal number of processors, the question that somebody asked is that what do we mean by the optimal number of processors, isn't it? That is the question. So, see, we have n number of tasks, okay, and some m number of processors, and the problem is that we need to assign this n number of tasks, divide this n number of tasks and assign them to the m number of processors, so that individually the processor loads are balanced. That is the algorithm, because this is being used for EDF, and if the number of tasks is small, we can try out all possible combinations of the tasks, right. What if T1 and T2 come to task processor 1 and T3, T4 goes to processor 2 and T5, T6 goes to n, all possible combinations of task partitions we can construct and assign to different processors and check which is the best combination of task which will make the load most balanced. That is the optimal.
Since it is dynamic algorithm, EDF.
No, this is not, see, the individual nodes are EDF, but the allocation is static. This is a static allocation algorithm, but the individual nodes are being run on EDF. Is that okay? Is that clear what is meant by a optimal solution that we are talking of here? Okay. Now, let us see how dynamic allocation of algorithms can be done. We will look at two algorithms actually. These will be required when tasks arrive asynchronously, where new tasks get created, aperiodic tasks, sporadic tasks and so on. So, once the task arises, needs to be assigned to a processor at that, after that time. Till that time we do not know what will be the state of the other processors when this task will arise and which will be the best processor. We do not know until the task actually arises, and at that time we need to examine which will be the best processor on which it can run. The dynamic algorithms, of course, they handle cases which cannot be handled by static algorithms, but they incur high runtime overhead, because the allocator component here has to keep track of the load position of every node. Based on that, it will make the decision. What is the current load of different nodes, it needs to keep track of, and based on that only it can decide where the task will run. So, here the algorithm is as follows. Every processor will maintain two tables. One table is called as status table, which is the tasks, it keeps track of the different tasks it has committed to run, the execution times and periods of these tasks. So, it is about its own status. The status table of a processor is about its own status. The other table is about the system load table is about the status of other processors in the system. So, one table it keeps track of what are the tasks it is committed to run, and the other is about what is the latest load position of all other nodes in the system. And of course, as we were mentioning that this will not be the current load position, it will be slightly stale obsolete information, because this will be obtained through some broadcast, and the broadcast can't occur every instant, isn't it? It will occur once in a while, and based on that it will update its table, and that load position it will assume until the next broadcast comes. So, in between two broadcasts, the load table will slowly become obsolete. The time axis is divided into windows, and the windows are basically fixed intervals of time, and at the end of each window each processor will do a broadcast. They will examine their own status table and find out that for the next window what is the fraction of processor time that is free at that instant. So, at the end of every window each processor will examine their own status table, find out that in the next window what is the fraction of computing power or processor time that is free. One thing, of course, we are implicitly assuming here that windows are the same for all processors. I mean, see, the time that every node has is the same time. If the time reading is 100 in one node, the all other node the reading is 100, but as we will shortly see, that assumption is not very correct actually. The nodes will differ by some extent, the times of different nodes will differ by some extent, and even if we try to synchronize the clocks, see, without synchronization of the clocks the times will be widely different. Even if we synchronize the clocks, still then the different clocks will be varying by some amount. But let us not get into that complicacy right now. Let us assume that every node at the end of the window, everybody knows when the window ends, and then they examine their own status table, and then they determine what is the time that is free for the next window, and then they broadcast it. And then every processor on receiving a broadcast from another node will update its load table regarding that processor. So, just see the complexity here, that every node, if there are 10 nodes, each node will broadcast to all other nodes, and those nodes, every node will also look at the broadcast received and it will update the system. For 10, what is the number of messages that will be sent? You can easily compute. Please try to do that. How many messages will be sent in this, in every window? Now, the algorithm works as follows. So, that was about keeping track of the table, right, about the system state table. Now, when a task arises at a node, we are saying that in distributed system tasks arise independently of each other. Now, when a task arises at a node, node first checks its own status table, local status table, to find out whether it can handle this, so that the time constraints can be met. If yes, it can handle this task, then it just updates its own status table. If not, then it has to examine the system load table to find out a processor which can best handle this task, and then it would have to migrate this task to that processor, and of course, it has to check whether the other processor can meet the deadline of the task, where it has to assume for migration of task it takes some time. Now, one thing is that it won't be as simple as this, just find it, consult its system load table and just send the task to that processor. It won't be that simple. It won't work actually if we do that. Just examine the system load table and just offload the task to that processor. Why is that? Is the question clear? The question is that if the node just examines the load table, find out the processors which can handle this task, that is the task can meet its deadline, find those processors and to one of them just migrate the task, it will not work.
So there will be a time duration between that analysis and then actually migrating the task to the
Migration we can assume a bound, a time bound, and that can be handled. A time bound.
By the time it uploads, other processor might have uploaded some other.
Okay. So there are mainly, see, he says that what if two processors have that same load table and they examine that there is a lowest loaded processor and both of them they decide to transmit the task to that processor. Yes, that is one problem, that too many tasks might come to the lowest loaded processor. The other problem is that actually the system load table, that is the global load table, that has obsolete information. So, because the load position changes instantly, some tasks get arrive, etc. Locally there might be some task which has arrived in that node, right. So, the load position that is there is obsolete, and whatever as per the current knowledge is the lowest loaded processor may not necessarily be true. So, that situation need to be handled. We can't directly offload the task to the lowest loaded processor, right.
That table is updated dynamically.
The table is updated once in a while, I mean periodically after a window. The window may be, let us say, 10 seconds or something, because if you update that window, if the window size is too small, then too much of message complexity overhead will be there, right. So, it has to be of some acceptable duration, 10 seconds or something.
How do we decide this?
That depends on system to system, like what the question is that what will be the size of the window. The size of the window depends on how much time does message take place in that system, how many nodes are there. So, basically some simulation experiments have to be conducted and then found out what is a good window time.
No specific algorithm.
You can't say that, see, this is the best window time, there is no such algorithm, has to be found out experimentally. Okay. So, we can't just offload the task to a processor which can handle it. So, we need to go for a bid. So, the node which finds that it cannot handle a task sends out request for bids by consulting its load table, finds out what are the lightly loaded processors which are called as the focused processors, that is the terminology used in this algorithm, finds out which are the processors which can handle this load. Handle this load means the time it takes to migrate the task and plus the task execution time that must complete within the deadline of the task. And after having identified the focused processors, it sends out RFBs about the task. The RFB will contain what is the execution time, what is the deadline, etc. to that task, that processor. and of course, by the time the RFBs arrive at the focused processors, there they might have become overloaded, then they will just ignore the RFB. But if they after the RFB arrives, if they find that they can still handle the requested task, they will send out bids. Okay, I do not have a slide here, but the bidding one. So, they will send out the bids, and once they send out bid to one processor, they can't send a bid to another processor, because they will reserve that slot for it, right. So, your question regarding multiple tasks getting transferred to one node will not arise, because once they send out a bid, they will not bid for another task, right. And the processor which is overloaded, which will examine the bids and then find out which is the best processor where the task will most likely to meet its deadline, it will transfer it there. And of course, those processors which had bidded at the end of the window, they will again know that they have not got the bid and they will reset their load position, right. Now, this algorithm incurs very high communication overhead. Why is that? Because two components. One is that the status messages have to be periodically transmitted. Every node broadcasts its own status and then they are updated. The other component of the overhead, communication overhead, is due to the focused addressing. So, it will send out RFBs. The request for bids will be sent out to the focused processors, and then the bids are made, and then the task is migrated, right. So, these are the complicacies in the communication. Two components, two main components, transmission of status messages, and also the RFBs are transmitted and bids are sent. And as some of you had rightly remarked that the window size is a very critical parameter for this, but we do not have any straightforward way to determine what is the window size. But what we know is that if the window size is large, then the communication overhead will definitely reduce, but the information will be obsolete. So, even all the processors which have been sent RFBs, they might not be able to accommodate the task, whereas another processor which was having high load at that instant might have become underloaded and it is not able to transfer to that task. So, the window size cannot be too large, because that load position could have considerably changed by that time. The underloaded processors might have become overloaded, overloaded processors might have underloaded, and the window size would depend on several parameters. One is the task characteristics themselves, like how many tasks arrive per time. It will also depend on what is the communication time, message transfer time. It will also depend on how many nodes are there, because if there are too many nodes, then too much of message communication will occur due to broadcast. So, the focused addressed and bidding algorithm has a problem of communication overhead. So, we have this body set algorithm which tries to overcome the communication overhead problem, the focused addressed and bidding algorithm. It is similar to that. You will observe that this is very similar in working, but you will see that the communication overhead here is much less. So, here it is very similar, it also will need to keep status table, etc., but it only differs in the manner in which the target processors are found. So, let us see this algorithm, the body set algorithm. So, here a processor can be in only two states, either it is underloaded or overloaded. There are variations of this body set algorithm also in the literature. You can find that some algorithms, they maintain three states. One is underloaded state, one is OK state, where they are neither too overloaded nor too underloaded, and then a overloaded state. Overloaded and underloaded, these are based on some threshold values. If it is more than, let us say 0.4, we will say that it is overloaded, less than 0.4 it is underloaded. Here no periodic broadcasts are required, and a node broadcasts only when its status changes from overloaded to underloaded or vice versa. So, this part of the communication is greatly reduced. Just check here, instead of sending messages every second or so, it just broadcasts only when its status changes.
No need of having that window.
No window, nothing is necessary here. The messages are sent asynchronously as and when there is a change in the status. And also, when the status changes, it does not really broadcast to all processors. It only sends it to a subset of the processor called as the body set. So, here also even see the number of times it has to transmit the status information is first of all reduced, and also it is not sent to all the processors, sent to only few limited processors which are called as the bodies. And of course, how to find the body set, how to design the body set, we will look at that. It should not be too large. If it becomes too large, it will become like broadcast. If it is too small, then it may not be able to send migrate the task to a proper node, because it will migrate the task only to one of its body. So, there might be an underloaded processor far away, but still it does not know about that, because it keeps information about only its bodies. In a multi-hop network, the body set is typically the immediate neighbors. So, this is a algorithm which is much more efficient, less overhead, but the thing is that the kind of solution that is obtained by the body set algorithm may not be as good as that by the focused, addressed and bidding algorithm. So, the highlights of this algorithm is that the node state is threshold based, it does not have to keep exact utilization values, only the overloaded and underloaded status is maintained, and a task on arrival is checked whether locally it can be handled, otherwise it checks the information about the body nodes, the body set, which are underloaded body set nodes, and tries to transfer them. The information policy, information exchange policy is based on the body set, and to the bodies are informed only when there is a change in the status of the node. And the transfer policy is, one of the bodies is chosen as the receiver, and it transfers the task. Now, let us look at another category of scheduling.
So, this dynamic scheduling
Yes.
algorithms what we are seeing,
Yes.
whether these are applicable to some EDF or RF or both or something. Like in static we had some.
Okay. Okay. See, the question that was asked is that this dynamic allocation, task allocation algorithm, do they work in conjunction with some specific local node scheduling algorithm? See, here we are not constrained about a specific algorithm being used as a local node, because the local node might be using RMA, EDF or DMA or whatever variation, we do not bother. What we are bothered here is that whether the local node can handle it or not, that is decided by the local node itself. So, the distribution of this, whether there is a flexibility here, that local nodes might be using EDF, RMA, etc., but they have to themselves run the test and say that, see whether they are able to handle the task or they need to transfer it elsewhere. So, that way this is much more powerful. Is that question all right, okay, fine. Now, let us look at fault tolerant task scheduling. Actually, we had said that one of the main advantage of using a distributed system is that we can incorporate fault tolerance very easily. Fault tolerance can be incorporated in many ways. One is have separate hardware, separate nodes dedicated, where you run the task, extra copies of the task called as the backup tasks, you run on some dedicated node, and when one node fails, that takes over. Or there can be a voting where they decide which node has failed. See, if we can't really decide which node has failed because it might be producing incorrect results, so then a voting solution can be adopted. But unfortunately, that solution has the extra hardware component that is built in into that solution, because we have a dedicated hardware and we are saying that the backup copies are running on that. On cost consideration, that is not a good solution. Can't we reduce the hardware cost? Can't we just run additional copies if necessary and minimize the hardware cost? So, that is about this task scheduling approach, fault tolerant task scheduling approach. Here, we will not run a task unless it is required. We will not have a dedicated processor just running these backup tasks, and also we know that the failures will not be frequent, just once in a while something will failure. So, we will have multiple backups assigned the same time slot, assuming that at best one of them will fail, and then that can run. We need not have time for all the tasks just running and wasting the resource, right. That is the idea here. Now, let us see how this works. So, this is the approach of obtaining fault tolerance through task scheduling rather than redundancy of hardware and running additional copies here. This is a very cost efficient technique, requires very little redundant hardware resources. So, here we schedule ghost copies. The ghost copies are basically backup copies. These are redundant copies of a primary task, and the redundant copies are not basically duplicate copies. These can be using different algorithm, it might be a more elementary solution, right, because see, once we find the primary task has failed, we will have very little time to run the ghost copy actually. That much time in determining the primary task has failed will have already passed, and then these are skeletal solutions, at least some result they will give. So, the redundant copies are called as the ghost copies. The ghost copies are not identical to the primary copy, they are stripped down versions that are executed in shorter duration, because by the time we determine that the primary has failed, we have already exhausted some time and the deadline will already be approaching, and we can only run some quick solution. And the main idea is here that the ghost copies of different tasks can be overloaded on the same time slot. So, we can have a processor on which some tasks are running, some primary tasks are running, P1 is running here, and on this slot the ghost for primary task 2, ghost for primary task 3 and the ghost for primary task 4 are all overloaded here. They are assigned to the almost the same time slot here, and this may be some primary 4. Now, the assumption that is implicitly made here is that all the primaries G2, G3, P2, P3, P4, okay, let me write P5 here. P2, P3, P4 will not fail at the same time. Only one of them at best can fail, and then what we will do is we will run only that ghost copy for which the primary has failed, the other ghost copies will be deallocated. But one thing is that the primary, a ghost for a primary cannot run on the same processor, because what if the processor fails, then the ghost copy is of no use, is not it? It can handle that fault of a processor failing. It can handle, of course, the task failing, a software fault it can handle, that this primary task had some difficulty, possibly the ghost will not have that problem. And also the other thing is that if the primary, we determine the primary will fail at, it will be known that the primary will fail at some point of time, then we could not have really scheduled the ghost along with the primary. See, the ghosts are scheduled overloaded with each other, the ghosts are backed up. A ghost cannot be backed up with another primary, ghost and a primary cannot be allocated at the same time slot, right. So, two constraints, one is that a ghost cannot be overloaded with a primary, and the other is that a ghost cannot run or should not run on the same processor on which the primary is running. Now,
Should it be the case always that ghost should not run on the primary?
on the same okay, the question is that let me get the question correctly. So, you are saying that is it a necessary condition that the ghost should not run on the same processor as the primary, is it? Okay. So, if the ghost is made to run on the same processor as primary, then some categories of faults we can't handle. For example, if there are problems with the processor, then the ghost and primary will both fail.
But if it is not a hardware fault, then
If it is a software fault, yes, but only thing is that we can't run it before the primary completes, is not it? We can't allocate the ghost until the primary completes. So, overloading will become a difficulty. So, unless the deadline is very long for the primary, we can't run the ghost along with the primary, is not it? So, there are some difficulties here, but normally a ghost is allocated on a processor other than the processor on which the primary runs. Okay. Let us proceed. So, if it is determined that the primary is successful, then the ghost is deallocated, the backup copy is deallocated. So, what will happen is most of the time the ghosts will get deallocated, and that much time for the processor on which the ghosts are allocated will remain idle. But see, the idle time we have reduced effectively. If we had dedicated processors running the ghost, the backup copies, then we would have too much of wastage of those processor times. Here multiple of ghosts are overloaded on the same time slot, and at best we are wasting a processor time equivalent to 1/3 or maybe 1/4 of the time. So, this is a very promising approach to achieve fault tolerance. Now, so far in all our scheduling algorithms and otherwise, we assumed that there are local clocks at different nodes and the clocks are all synchronized. So, each node has one clock, that is true for every distributed system, and we made an implicit assumption that the clocks are synchronized. The clocks, first let us see the use of this clock in a distributed system. It is used for all the purposes for which a uniprocessor uses a clock, that is for determining the task deadlines and for finding when to take off scheduling, clock based scheduling, all those things the clock is used. But besides that, it is also used for determining message timeouts, how long clock processor needs to wait for a message, and also for time stamping, because when messages are sent out they are time stamped. But why do we need to do time stamp of the messages? Time stamping is done to give the receiver an idea about the age of the message when it was transmitted, so that can be used for ordering the messages or to determine whether the message is too obsolete to be rejected. So, typically all messages sent in a distributed system are time stamped. In any practical system, the clocks at the individual nodes tend to diverge. It is unlikely that two clocks would run at the same speed. Why is that? Why is it that two clocks will not run at the same speed? Anybody would like to answer this question?
Manufacturing differences and also there can be a drift between the working of two clocks.
No, manufacturing means not clear actually. So, how are the, so first let us understand how the clocks work. Somebody said that manufacturing problem may be there, but first let us understand how the clocks would work. How will they derive the time?
So there are actually quartz crystals.
Yeah, these are basically crystal driven. Those principle of almost all clock, even the clocks that we are using are all crystal clocks, isn't it?
Olden days clocks were not like.
No, that no olden days spring clock etc. No, there is nobody uses now. Not even persons use. So, about computer systems, definitely not. No computer system will use a mechanical spring clock, right? They will use a quartz clock or a crystal clock. So, then why should the time diverge? These are quartz oscillators basically. So, why should they diverge?
Because of that some drift in that. It may be having some drift and so.
Now, which will have drift? Why should it have a drift? These are all quartz clocks. Why should have the drift?
Drift can be because of its properties, because two things cannot be exactly same.
And any other answer? He says that two things cannot be same. Okay, you can investigate more, but the thing is that the quartz oscillations, which are very high frequency oscillations, they also depend on parameters like temperature of the quartz, the pressure, and many other parameters are there, based on which the quartz frequency can vary. If it is heated, it will, its frequency might increase and so on. So, different places will have different conditions, and the quartzes, even though these are quartz clocks, they will differ by a small extent, and that small extent, if it varies for every time pulse, then it is large because we use a large number of pulses, no, gigahertz clock, we use a large number of pulses, and each pulse differs by even a small amount, we will have a large variation. So, the clocks, they drift. So, even if we have to start with, we had synchronized them, as time passes, it becomes 1 hour, 2 hour, 1 day. The difference in the time reading keeps on increasing every time, that keep on diverging. So, the clocks will diverge more and more as time passes, because they run at different speeds. And this lack of synchrony is called as a clock skew, that is the term we will use. The skew is basically the difference in time reading between two clocks, that is how we will define a skew. Skew is the difference in time reading between two clocks, and the skew will increase with time only. And after the increase, see, if it was a constant, if the skew was constant, like one clock differed from the another clock by 1 second, we can, upon receive, we can subtract that 1 second and then find out the time, but unfortunately the skew is not constant, it keeps on increasing, and therefore, the time out, time stamping, all those operations will become meaningless because of the skew problem. So, we will discuss how to make the clock synchronized. We will look at some algorithms, we will look at their complexity and what kind of problems they can handle, they will not be able to handle, which one to use, etc. We will look at that in the next class. Okay, thank you.